Welcome back to section 3 of chapter 10. This section is on polar coordinates and the calculus involved in using them. This first part is just a review, possibly, maybe a brand new introduction to what polar coordinates are. The second part will have the calculus for polar coordinates.
Called a polar graph, which looks kind of like this. The origin is also called a pole. We have a polar axis, and then we have two coordinates. We have a radial coordinate and an angular coordinate. That would be r comma theta. And what each point is instead of x comma y, each point is going to be a distance away from the origin, and then an angle measured just like we measure angles, starting at our positive x-axis and then going counterclockwise. And so that's how we measure, or how we signify points. And so if we were going to plot a few points on these graphs, we could plot the point P. It's going to be 3 out, so we're going to be on the third ring, and then 5 pi over 4. So we have 1 pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, 5 pi over 4 is here, then 1, 2, 3 out. There. That would be point P. Now the thing with these points is they're not unique. We could write this different ways. For instance, the radius could be negative. If we were on this other side at pi over 4 with a negative radius, we could have p is negative 3, comma, pi over 4. That would get us to the same point. Another thing, we could go around the circle again. So instead of 5 pi over 4, or we could go backwards, we could have 3 comma negative 3 pi over 4 would get us the same point. So these points aren't unique like they are on the coordinate system. However, dealing with circular stuff, this is a lot easier to be able to do that with. Couple more points. We have negative 2 comma 7 pi over 4. So 7 pi over 4 is this guy. We want negative 2, so we're going to go 2 in the opposite direction. 1, 2. This would be Q. Other ways of writing that, we could have 2 and then 1, 2, yeah, 2 and then, oh yeah, it is 3 pi over 4. We could have 2 then 3 pi over 4, which I think that 5 pi over 4, 7, give us negative 1, 2, 3. Yeah, no, it's looking right. So I'm thinking I made a mistake somewhere. I probably did. Find it and correct me. So that's one way, or we could do, oh, there's, no, 7 pi over 4. That's there. 3 pi over 4. Yeah, I don't know. We could also go with negative 2, negative pi over 4. Because we could come backwards pi over 4 and then go negative 2 instead of going around the full circle. Or we could have point R. Here we're going negative 3 pi over 2, which takes us here going backwards. 1 pi over 2, 2 pi over 2s, 3 pi over 2s, and we're up 4. 1, 2, 3, 4. that point right there, which could be, we could be at -4, and then only going back to the 1 pi over 2, or we could be +4, but going forward to 1 pi over 2. And so, different ways of graphing each of the points, or different ways of writing each of the graphed points. So, how about converting between Cartesian and polar coordinates? What can we do there? Well, we're on a circle, like a unit circle. We've dealt with circles before in the past, and what we do is we make triangles. And so we make triangles. We know that cosine will equal x over r. So cosine theta equals x over r, and sine theta equals y over r. We multiply the r over to get x equals r cosine theta and y equals r sine theta. That's how to go from um, from polar to Cartesian, because we have a theta and we have a radius. You do the radius times cosine theta to get x, the radius times sine theta to get y. To go backwards, we need to find the r. So we would use the Pythagorean theorem because we would know x and y. So we can find r. And then this angle is going to, the tangent to the angle equals y over x. So using this bottom set is what would take us from Cartesian to polar. So this is just spelling it out a little bit. So if we want to go from polar to Cartesian, x will equal 2 times cosine of 3 pi over 4, and y will equal 2 times sine of 3 pi over 4. So cosine of 3 pi over 4 and sine of 3 pi over 4 are both going to be root 2 over 2's. Cosine, however, is going to be negative. So x would equal negative 2 times root 2 over 2 is just negative root 2. And y would equal positive 2 times root 2 over 2, so root 2. So the point in polar 2 comma 3 pi over 4 in Cartesian would be negative root 2 comma root 2. Going backwards, we have 1 negative 1, so r squared will equal 1 squared plus negative 1 squared. So 1 is 1 plus 1, so r squared equals 2. So r will equal root 2. And then tangent of theta equals negative 1 over 1. So equals negative 1, whereas tangent going to be negative 1. Tangent is negative 1 at the at 3 pi over 4. So theta would equal 3 pi over 4. And so we'd have root 2 comma 3 pi over 4. And these are generally, like, we're going to use nice angles that you know because you know how to use unit circle. You do. So how do we graph in polar coordinates? Some basic curves. Some of the most basic would just involve one variable. R equals a number. Well, if the radius equals a number, and it doesn't matter what theta is, that gets us a circle of that radius. And most of our equations in polar will be r equals a number with theta. So r is like the y, theta is like x. What if we go the other direction, which would normally get us a vertical line? Theta equals something. So we have an angle, but the radius doesn't matter. Well, the angle is just gives us a direction, and so theta equals something gives us a line through the origin at that angle. And then what if we have both? Let's say r equals theta. So the radius will equal the angle. So as the angle is getting bigger, the radius is also getting bigger, which gives us a spiral. The radius equals the angle is a spiral. Other basic curves. Let's convert the equation r equals 6 sine theta to Cartesian coordinates so we can describe what this thing looks like. Because when we see like r equals 6 sine theta, what does that even look like? So, how we can change this to Cartesian. First of all, everything we have like r cosine, r sine. So let's multiply both sides of this by r. That'll get us r squared equals 6r sine theta. Well, remember that r squared equals x squared plus y squared, and y equals r sine theta, so we can substitute those in. Instead of r squared, x squared plus y squared equals 6r sine theta is just y. So we have x squared plus y squared equals 6y. Well, let's get this. This looks a lot like some sort of conic section because we have x squared and y squared. We get those into standard form by completing the square. So let's move that 6y over. We get x squared plus y squared minus 6y equals 0. X squared, this is ready to complete the square because the y squared's by itself. So we're going to have something squared equals a number. It'll be y minus, we divide this number by 2, so it's 3. And then we square that and add it up in that upper equation. If we add 9 there, we also have to add 9 there. So this becomes a 9. So we have x squared plus y minus 3 squared equals 9. That is the equation of a circle. It's the equation of a circle with center 0, 3 and radius of 3. So if we graph it, it looks like that. We can generalize this. So if we generalize that, we could use, instead of the 6, we could use a. When we have r equals a, it's just centered at 0, 0 with radius a. When we have r equals 2a sine theta, it's centered up a, so the 2a would be that whole diameter there. So this half distance is just half of that number. So we had 6, that was 3. The diameter was 6. And if we use cosine instead of sine, it moves it on the x-axis instead of the y-axis. Notice all of these, it's on an axis, and the circle hits the origin. So we're not moving the circle anywhere we want quite yet, but we can get it off of the origin a little bit. More graphing. So to graph in polar coordinates, it's the same thing that we would normally do to graph anywhere else. We are going to plug in some points. So we have r equals 1 plus sine theta. let's plug in some values for theta. Sine theta will make one full rotation in 2 pi. So we're going to go from 0 to 2 pi here. Plugging in points, I would use not necessarily even all the points on the unit circle. I would use the ones that we can find easily, like the ones that end up being 1/2 as opposed to root 2 over 2 or root 3 over 2. And so those would be the pi over 6s. So if we plug in these points, plug in 0, sine of 0 is 0, plus 1 is 1. Plug in pi over 6, sine of pi over 6 is 1/2, plus 1 is 3/2. Plug in pi over 2, it's 1, plug it to get 2, then it starts going down, 3/2, 1, etc. You can plug it in and see those values. Notice at the beginning and at the end, it's equal to each other, which means it'll connect. And so now we could plot these points. We have the radius over on the right and the angle on the left. We can plot those points on our polar graph and then connect the dots using a smooth curve. We're not going to connect the dots using straight lines, but use a smooth curve to get something like this. You have our points on there, and then it just connects. The more points you do, the more accurate you get. But we have this, which is a cardioid. So that's how you can graph using in polar coordinates. It's just finding the points. And that's one way. There's another way, which would be using Cartesian coordinates. That was supposed to zoom in, or supposed to fade in. So using Cartesian coordinates, we would graph it with theta as x and r as y. And then we would take each of the pieces, each of the sectors of the circle, and we transfer that to the polar graph. So if we're looking at this one, we go from 0 to pi over 6, and the y value, or the r, goes from 1 to not quite 2, but like 1.5. So we start out radius 1, we end up radius about 1.5, and we connect it with a smooth curve. Then we do the next piece of it. It gets to radius of 2 and the angle of pi over 2. So we'd put the dot there, and we connect it with a smooth curve. And we would just keep doing that going around. Sometimes this is quicker because you can graph, like this one was just sine of theta, we just moved it up 1. So we can do that translation. We can get this original graph pretty quickly here, and then we can change it to the polar just piece by piece. This is something, it takes a bit of practice, but it is something that gets to be doable. That's doing the same thing. So we could graph the polar equation r equals 3 sine of 2 theta. So we can graph 3 sine of 2 theta. We're going to have an amplitude of 3. The period's going to be shortened. It's going to look kind of like that. And when we graph it, remember the y value is the radius. So every time it hits the axis, that means it's going to hit the origin because the radius will be 0. So we're going to start at the origin, the first quadrant. We're going to get big and then go back down. So the first quadrant got big and then came back down. Then the second quadrant, we get big in the negative direction. So it actually is taking us out there. And then the third, we get big here, and the fourth is there. So this is weird because it does the first, and then the fourth, and then the third, and the second, and then it would keep going if we extended it to 4 pi or however many pi we wanted to use. But by seeing that, hey, this is going to go out to 3, so in our circles, we'd go out to the third one, and it just took it up there and came back down, and took it up there and came back down. So we can do that quickly without having to graph every single or plot every single point. And then matching polar and Cartesian graphs, the butterfly curve. Designed for that, I had a nice fade here so you could see this is why it's called a butterfly curve. You can graph a butterfly. But it gives us that. And then our Cartesian graph over here on the left, we can follow what it's doing. So starting here, we can, and so that would be just plugging this in. We could graph this as just as y equals e to the sine x minus 2 cosine 4x. That would give us this graph. Then we can follow. So when theta equals 0, we're at -1. So theta equals 0, we're over here at -1. And then we hit the origin every time we hit the axis. So B is at the origin. So we start at A, we go to the origin, then we're going to go out to 4, way out here, and then back down, but not all the way. We get close at pi over 2, but not all the way. It's there, then it goes back up again. And then it'll come back to the origin at F, a little bump out for G, back to the origin. And so you can follow the graph, and that's actually all this one was having you do, is follow the points. And finally, using graphing calculators. Wouldn't it be nice if our graphing calculators would help us out with this? At the very least, to check answers. Well, they do. Just change the mode setting, just like you did for parametric. Go over to polar. It'll automatically change to r equals. Your variable will automatically give you a theta instead of an x, a y, or a t. But we can graph, so we could consider the closed curve described by r equals cosine of 2 theta over 5. And so you could plot that. You could pause me right now if you wanted to plot it, see what it comes up with. But we want to graph the whole curve. The closed curve means that it's going to connect to the starting point. So we want the starting point to equal the ending point. The starting point, when theta is 0, we get 0, so cosine of 0 is 1, so r will equal 1. So we're going to want an ending point where we have 1, 0. So the next thing that's going to equal 1, we need cosine of 0, we need cosine of 2 pi, we need cosine of something like that. So 2 pi over 5, or 2 times theta over 5. We need that to equal about 2 pi, so we can multiply, divide. We get theta equals 5 pi. So we plug that in, that gets us the 1, but when we graph that, 5 pi, it doesn't close. It's only half. So we could do another half to get to 10 pi, and that will get us the full complete graph. And this could all be done on your calculator. You can play with it. If you go too far, it'll overlap, which isn't a problem if you're looking for the graph, but if you're just giving an interval, you'd probably want the shortest of the intervals. So this is polar coordinates. Very interesting. Uh, Again, this is just the introduction to polar coordinates. We're not doing calculus on it yet. That will be next time. Um, so you want to practice this. Um, keep working problems, keep asking questions, and as always, happy mathing.